Good afternoon, and welcome to Mr. Fish's pre-algebra class. Today, we're going to cover lesson 3.1, understand relations and functions. And I gotta tell you, I think that last chapter kind of kicked our tails a little bit, right? There was some rough stuff in that one. So this one I am predicting is gonna go a little smoother. I'm not just saying that to try to pump you up a little bit. I really think it's going to be okay. And several people told me after last hour they like what we did today way better than what we've been doing. So here we go. Today we are going to identify whether a relation is a function. First thing we got to do is figure out what a relation is, right? We talked about relations a little bit, I think, but we're gonna go back and review that, and then we will also interpret functions, what those mean. Okay, here we go. Our warm-up question: 10 members of the photography club want to raise $500, so they will hold a raffle with donated prizes. Jesse proposes that to reach their goal, each member should sell 50 raffle tickets. Alexis proposes that each member should raise $50. Whose plan would you recommend and why? Rudy.
I would go with each member should raise $50 because with 50 tickets, if they buy the $20 option, then they'd be losing money.
Okay, so that's a great explanation. If we are selling 50 tickets, if that's our goal, as long as we only sell one ticket at a time, are we going to be okay?
Mm-hmm.
Yeah, because then every person would raise $50, and that would get us to our goal of 500. But if I sell 50 tickets and somebody buys 20 tickets, then I only get 20. Or sorry, if they buy 25 tickets, now I get $20 for those, and that's going to lower the total amount of money that I raise. So then in the end, we might only end up with $400, and we didn't meet our goal. All right. So that's kind of a real brief look at what a relation is and and even what a function would be if we wrote those out as equations and graphed them and stuff. So that's the kind of stuff we're doing to interpret functions today as we move forward. All right. So let's look at our first example. Jonah. Next page, 166. And this one, there's not a whole lot of writing for you to do today in your workbooks, but boy, you need to pay attention to a couple of these things, just definition-wise, because understanding what's going on is going to be important. So Jonah is shipping 5 boxes for his uncle. Each box is the same size but a different weight. The cost to ship each box is shown. Should Jonah expect that the cost to ship a 15-pound box will be a unique cost? What do you suppose that means, a unique cost? Maddox?
Not the same.
Not the same as the other costs, right? That it would be a different number than the numbers that we already have for cost. That's a good way of saying it. So it's not the same cost. So based on what you see there, do you think he should expect a 15-pound box to be different than the others? Why would you think that?
It's not the same weight.
Because none of the others are the same, right? Every time the price or the weight goes up, what happens to the price?
It goes up.
The price goes up. So you would expect that if the boxes keep getting bigger, the prices keep getting bigger. That's kind of the way it looks, right? And so that's exactly what they do here for us with this slide. They show us using structure. So structure just means, what does it mean to use? What is a structure? What do you think of when you hear that word, structure? Any thoughts at all?
Something to hold something up.
Okay, something that holds something else up. So like, I think of like a scaffolding. Do you know what scaffolding
Yeah,
is?
that's what I was-
Okay, so like if you're building a building or painting a house or whatever, they put scaffolding up on the outside so that you can get up to those top floors without having to climb ladders and stuff, right? So that's a structure, and that structure gives support to what you're wanting to do. So using structure just means giving it a framework, giving it skeleton so that we can hang our information on it. And what they did here was they put the biggest box on the bottom, and they just smallest box on the top, and they showed it like that. So is there a relationship between the weight of the box and the cost to ship the box? Yes. Sure. How would you describe that relationship? Achilles.
Each pound adds more.
Okay, so every time the weight of the box goes up, the price goes up. What kind of relationship would that be? We're gonna get there. We're not quite defined what a function is yet, but think about a graph. As the weight of the boxes goes up, what happens to the cost? It goes up as well. So what kind of relationship is that? Maybe this could be proportional, or it could not be proportional, but that's not what I'm looking for. When they go up this way, what are they?
Unit rate.
Starts with P. Positive. It's a positive relationship. Okay? As the weight goes up, the price goes up. It's a positive relationship. All right. So, next slide. Now organize the data into ordered pairs, and it's represented by these words input and output. And those are going to be very important words for what we're doing over the next couple of lessons, input and output. But here's the deal. There's no secret to it. It's not like a brand new type of thing that we're learning. All we're talking about is the X and the Y value. Input is always the X value, and output is always the Y value. And so when we look at our ordered pairs, which we have here, every one of them has an X value, right? And every one of them has a Y value. And so that means every one of our ordered pairs has an input and an output. And whenever we're talking about functions, input and output is the way they talk about X and Y. Input is the X and output is the Y. And so organize the data into ordered pairs. They already do that for you in this problem in your book. I just copied it onto the slide. So this is the steps we'll take. And then here's kind of the new thing. This is where it gets kind of new. Use an arrow diagram. Okay, an arrow diagram to match each input value to its output value. So notice what they did. Where did they get these numbers? 8, 9, 10, 12, 14. Where'd they get those? It's the X values, right? It's this group of numbers right here. And then where did they get these numbers?
The Y value.
Those are the Y values. And so they have the inputs, right, and the outputs listed separately in these little oval boxes. They have the inputs and the outputs listed separately. Now, what is this thing called? An arrow diagram. What would you expect an arrow diagram to have?
An arrow.
Arrows, okay? Now, in your book, they've already got this filled out, but for me here, all I need to do is draw those arrows. And how did I decide where the arrows go? Rudy.
You put them with the same thing for those.
Right, I just matched up the ordered pairs. 8 goes with 8.56, so I drew an arrow from 8 to 8.56. 9 goes to 8.72, so I drew an arrow from 9 to 8.72, and so on. So, listen, I mean, that's really is part of what we're doing today, is taking a list of ordered pairs and using that list of ordered pairs to create an arrow diagram. Have I lost you yet? Is that going to be fairly simple? Okay, all it is transferring data from one form, a list of ordered pairs, to another form, an arrow diagram. All right, now what's the whole point of an arrow diagram? What does that show us? Well, here's the definition. This is the new thing for today. A function, a relation is a function when each input is assigned exactly one output. This is the definition. You need to understand and learn this definition, because this is going to be one of those things that they're going to ask you this question over and over. Is this relation a function? And you're going to say yes or no. And when they say explain, you need to be able to explain it as either the input has more than one output or the input only has one output. Cooper.
So it's only a function if one number goes to the other number, like you can't have two numbers going the same.
Okay, that's a great question. And notice that it's defined in terms of the input. So we're always gonna be concerned with the input. That's our main concern. Input is where we're gonna focus. Okay, and when I look at the input, do any of my inputs have more than one arrow? All of my inputs have one arrow, right? The 8 has one arrow, the 9 has one arrow, 10, 12, 14. They all have one arrow. That means that each input has exactly one output, because I only have one arrow going from the input to any of the outputs, okay? So that's where I'm looking, is the inputs. And that means that yes, it is a function. So this is a yes, it's a function, and it's a function because each input has exactly one output, okay? All right. So that's the whole point of that top half of that page, is just being able to figure out this definition. So here we go. Let's move on and look at some other examples. So down at the bottom of the page there, Joe needs to advertise his company. He considers several different brochures of different side lengths and areas. He presents the data as ordered pairs. Joe is a weird guy, but okay, whatever he needs to do to think about advertising. So we've got some blanks in our arrow diagram here. These numbers are our inputs, right? And these numbers are our outputs. So what numbers am I missing? 4 and 8, okay? And we got those numbers from this list of ordered pairs here. I was missing this 4 and I was missing this 8. So now I just need to complete the arrow diagram. So 4 goes to where? 4, I need an arrow from 4 to 24. Then 5 goes to 35. And 8 goes to 24. And 9 goes to 27. Okay. All right. Really think about it. Is the area of a brochure a function of the side length? So does this arrow diagram represent a function? This is where it's a little bit tricky. Go back to this one. What did I say we have to think about? What do we care about? We're looking at the inputs. One arrow, one arrow, one arrow, one arrow, one arrow. Look at this one. Look at your inputs.
No, because there's 2 arrows on 24.
But look at your inputs.
Oh, so yes. Here.
Look at your inputs. One arrow, one arrow, one arrow, one arrow, one arrow.
So as long as the input has one, each of them
We
have one,
care,
only one.
we care about the input. As long as the inputs have one arrow, it's a function, okay? So this is a function because when I have to explain, I could simply restate the definition. Each input has one output. I don't care that this output has 2 inputs. That doesn't matter. What I care about is that each input has one output, okay? That meets the definition. We good? All right. Let's keep going. That one's tripping everybody up today because it's new and you see 2 arrows and you automatically think, oh, can't be a function, but you got to look at where the arrows are going, where they're coming from. All right, let's talk about this one. So Frank records the ages and heights of the 6 students he tutors in a table. Our first step is to create our arrow diagram, okay? And so what goes in my input side?
9, 10, 9, 8, 9.
Okay, 9, 10, and then we don't repeat numbers. So I'm not going to put 9, 10, 9. I'm going to put 9, 10, 8, 12. And then don't repeat the 8. And then here, 54, 61, 45, 65, and 50. Now I can make my arrows, so 9 goes to 54, 10, to 54, 8, 45. Oh, I missed one. This 9 goes to 61, 12 goes to,
65.
and 8 goes to 50. Okay, so is this a function?
No.
Why not?
What is this? Like,
Input
there's
has
two with two
those
arrows.
two.
Right.
Arrows for-
Because this 9 has 2 arrows, this 8 has 2 arrows. Okay? And since they have 2 arrows, it's not a function. Now, does that mean he needs to like kick one of the kids out of his tutoring session?
No.
No, it's nothing wrong with the data. The data's okay. It doesn't matter that it's not a function. It just doesn't fit the definition of a function. All right? And that's going to matter later when we get into writing some equations and things. But it's okay, it's not a function. It just doesn't fit the definition of a function. All right. Now then, what if he takes those numbers, and it's the same numbers as was on this one, and we're going to reverse the input and output. We're going to make the input the output, and the output the input. We're just going to switch boxes. Okay? So if I make my new input output table or my new arrow diagram 54, 61, 45, oops, it's a 4, 65, and 50. And then ages would be 9, 10, 8, and 12. So 54 goes to 9 and 10. 61 goes to, oops. 61 goes to 9, 45, 8, 65 goes to 12, and 50 goes to 8. So is that one a function?
No. 54.
Because of 54. So, you know, they did that just to give us another example of seeing not a function. If you reverse the numbers, it doesn't change what it is. Okay. All right, there you go. And note it. Okay. Here it is. This is what I want to point out on this one. Is age a function of height? On the last one, well, they didn't say it that way, but when they ask this question, is age a function of height? We want height to be our input. Okay, when they ask that question, is age a function of height? Height is the input. Is speed a function of time? They want time to be the input. If I reverse it and say, is time a function of speed? Now speed becomes the input. Okay, you gotta look at how they word the question, because sometimes when they give you tables like this, it's not obvious which one needs to be the X and which one needs to be the Y. And so you look at the way the question is worded. And so this one is always the input, and the other one's always the output. All right. So Heather and her parents, I got bleeped. Heather and her parents are going to an art museum for the day. The parking garage near the museum charges the rates shown in the sign. Is the cost to park a function of time? Is cost a function of time? So which one's my input? Time's my input, because it comes at the end there. So, you know, instead of drawing the little arrow diagram, is it okay if I just do this? Okay, so that can, you know, we can take a little shortcut there, and I'm okay with that. So is this a function? Yeah. Every input has a different output, right? 1 hour is different than 2 hours, and 2 hours, I've only got one output for each of those inputs. So yes, it is a function. Next question is, if they stay at the museum for 6 hours, should they expect to pay more than $25?
Yes.
It would make sense. Now, do we know it for 100% sure? Are you willing to like risk all your fame and fortune in life on it and stuff? I wouldn't risk much on it, because you never know. They might close after 6 hours, and then you have to wait till the next day, and then it was overnight parking.
I'm just a kid, I don't have much, so I'll
Yeah.
put it all on.
You're gonna wager it. You don't have much to
Yeah.
lose anyway. All right.
I have
All
like
right.
5
So
cents.
I have 5. That's all I could wager is 5
Yeah,
cents
I bet
anyway.
$10.
All right.
Yeah,
Well, you never know. you might win.
Eh,
All right, so, but it is reasonable to expect that you would pay more for 6 hours based on the information that we have. So the answer is yes, you would expect to pay more. Now, Heather claims that she can tell exactly, that's a key word, exactly how long a family was at the museum by how much the family pays for parking. Is Heather correct?
no.
Yes.
Oh, let's clear the room and duke it out here right in the middle. One says no,
Oh,
one
yeah,
says
beat
yes.
'em up.
Why do you say yes, Rudy?
I say yes because each one is different. So 1 hour goes to 5, 2 hours go to 10, 3 to 15, so on.
Okay,
So then if it were like, if they paid like $17, they probably stayed for like 3.5 hours or something.
oh, you're kind of reading between the lines, so to speak, and thinking that there's a $17 option in between 3 and 4 hours, okay? So, Cooper, why'd you say no?
Heather's saying she can say exactly how long she was there, like to the minute, based off how much they pay. How is she gonna know how much they pay in the first place? We've been
What?
there for hours.
Okay, well, if you tell them I paid, X number of dollars, would you know how long you stayed? The answer, at least book-wise, the answer was no, because this is the pay scale, or the cost scale, and we're not assuming that there is in between, like 2 hours and 10 minutes is $10.75 or something. So we don't have in between numbers. We're not going with a prorated scale. So you're either paying $10 or you're paying $15. So if you pay $15, how long did you stay? Well, it could have been exactly 3 hours. It could have been 3 hours and 10 minutes. Could have been 3 hours and 50 minutes, because it just wasn't 4 hours yet. So could have been, and 59 seconds. Right? So, so we're gonna go with no. And the whole thing there is when you're interpreting functions, we can't read things into the data that we don't know for sure. We just don't have that information. We don't believe that we can tell exactly how long it is. All right, so let's do a couple of samples. Well, this is the summary. The big deal, guys, is the definition. The definition is here again. A relation is a function if each input corresponds to exactly one output. You need to learn that, learn it, love it, live it, okay? And then you need to be able to look at examples and tell if they're functions or not. Is this first one a function? Yes, because each input has exactly one output. Is this one a function? No, because there's one input, 2 is the input, and it's got more than one output. It's got a 4 and a 6, right? So you gotta learn to recognize those and see those. Basically, what I've always said in the past, always look at your input first. Look at all your X values. If any of them repeat, then you gotta check it out and see if it's a function or not. If none of them repeat, 1, 3, 8, 5, 7, well, it's hard to tell in an arrow diagram because it might have more than one arrow going from it. But in a list like, well, let me get down here. In a list like this one, look at your input. You've got 3, 4, 1, 5, 2. Do any of them repeat?
No.
Automatically a function. I don't even have to worry about anything else. If the input doesn't repeat, automatically a function. Okay? Achilles?
What about negatives?
Negatives are just numbers. They're,
It's just a-
yeah, you just treat them. So if we put a -2 on there, 2 and -2 are different numbers. It doesn't, so that would still be a function, okay? Because, and it wouldn't matter what this was. If this was a 5, doesn't matter that let me do even like a 6 here. So +2 goes to 5, but -2 goes to 6, that's okay. All right, still a function. All right, good question. I kind of got out of order here. Let's do this one. Is this a function? No, because 20 goes to 2 different numbers, all right? We already did number 5. Number 6, is that one a function? What do I look at first? Look at the X values. Do any of them repeat?
No.
Nope. What does that mean? Function. I don't have to look at the Y values then. Okay? If the X values don't repeat, automatically have a function. All right, your assignment, pages 169, 170. Due tomorrow.